Hello everyone, this is Dr. Lennon, and today we're going to look at the method of integration by substitution. So far we've looked at integrating some basic types of functions, polynomials, exponential functions, logarithmic functions, things like that. But when you have these functions kind of combined via composition, we don't have rules for evaluating them. So that's where the substitution rule comes in, and kind of the idea is this is to kind of use the chain rule from the derivative in reverse. So we're using the same thing from the chain rule from the derivative in reverse. Now, I think the best way to look at this is to just kind of jump in and see a few examples. Really what you're looking for your substitution is you're looking to pick something so that the other factor it looks like that when you take the derivative. So let's look at some examples. So let's suppose that we wanted to compute the integral of 2x times the square root of 1 plus x squared dx. So the thing is, if you look at 1 plus x squared, you might notice that the derivative of 1 plus x squared comes out to 2x. So that's the substitution, and sometimes this is known as u substitution. Typically people use u as the letter for the variable substitution. So we let u equal 1 plus x squared, and then du will equal 2x times dx. So a lot of times what I do here is I just solve for dx, and you can notice that du is actually going to replace 2x and dx, or some people like to explicitly solve for dx. So if you would do that, you would solve divide both sides by 2x, and then you would have du over 2x that's equal to our dx. So then we can basically use u to replace 1 plus x squared, and we can replace dx by du over 2x. And let's see what happens. We have our integral now, and our integral becomes the integral of 2x times the square root of u, and then we can replace our dx by du over 2x, and so our 2x's cancel out. And so now we just have the integral of the square root of u, which we're going to write as u to the 1/2 du. And remember, when we're integrating some power like this of a variable, that's all we have to do is add 1 to the power and then divide by that number. So if you add 1 to 1/2, you would get 3 over 2, and then dividing by 3 over 2 is the same as multiplying by the reciprocal 2/3. And then we have plus c for a constant of integration. And then because the problem originally started in the variable x, it's customary to switch u back to what it represented, which was 1 plus x squared. So our antiderivative here is 2/3 times the quantity 1 plus x squared raised to the 3 over 2 plus our constant of integration. And that is the general antiderivative there. Okay, let's look at some other examples. So that one was fairly straightforward. So we just want to compute each of the following integrals. So we'll have a couple. So A, let's say we are computing the integral of x cubed times 2 plus x to the 4th raised to the 5th power times dx. Now, theoretically, this one you could actually do without substitution. You could multiply everything out, but then you'd have some huge polynomial with maybe 5 or 6 terms, and it would get kind of messy. But substitution allows us to do this in a much neater way. So again, notice if you look at the derivative of 2 plus x to the 4th, you're going to be left with 4x to the 3rd. So we can see that that kind of is going to take care of that x cubed out in front. So that's what we want to let our variable substitution be. Let u be 2 plus x to the 4th, and then du is going to be 4x cubed dx. We're taking the derivative of both sides. And then what you want to do is you want to divide by 4x cubed to solve for dx. So now we have du over 4x cubed is the value of dx. So we can plug all that back into our integral. What's going to happen? Well, we're going to have this integral of x cubed, and then 2 plus x to the fourth is replaced by u. That's raised to the fifth power, and then we replace dx by du over 4x cubed. So the x cubes will cancel out, and we'll be left with the integral of 1/4 times u to the fifth du. So now we have an integral completely in terms of the new variable u. And again, what we're going to do is we're going to take that u to the fifth, it becomes u to the sixth, and then we're dividing by 6 now. So 1/4 times 1/6 is 1/24. So we get u to the sixth over 24 plus our constant, and then we just want to switch u back to what it originally represented, which was 2 plus x to the fourth. So we have 2 plus x to the fourth over 24 plus our constant of integration. Okay, so same sort of thing. You let u be the thing that you recognize as when you take the derivative, it's another factor in the integral that you're looking at, and then just kind of follow the same recipe. Now some of these can get trickier, but a lot of times for the simple ones, it's pretty obvious what the substitution is going to be. So let's look at another. Let's say we're doing the integral of, let's say, x squared over the square root of x cubed plus 2 dx. So again, our variable substitution, we want to let be x cubed plus 2. So then du is just 3x squared times dx, the differential for x. Divide both sides by 3x squared. And we have du over 3x squared is equal to dx. So now we have the two things. We have u solved for and dx solved for. Those are the two things we need to rewrite our integral in terms of u. So we have the integral of x squared over the square root of u times du over 3x squared. So the x squareds will cancel out, and we're just left with the 1/3, and u, 1 over the square root of u is the same as u to the negative 1/2, which is the easier way to write this to find the general antiderivative. So when you add 1 to the power, you're going to get u to the positive 1/2, negative 1/2 plus 1 is u to the 1/2, and then dividing by 1/2 is the same as multiplying by 2. So we get 2 times 1/3, which gives us 2/3, plus our constant of integration. So this is going to leave us with 2/3, change u back to the original x cubed plus 2, and let's change the 1/2 power back to a square root. So we have 2/3 square root x cubed plus 2 plus our constant. Okay, let's look at one that we can do kind of in two ways. So this one comes up a bunch. So there's kind of a sneaky algebra way and also a u substitution way. So let's look at the example here. Let's say compute the integral of x over x plus 5 dx. So I'm going to do this one by two methods. So method 1 will be via u substitution. So the way we're going to do this is, it's kind of complicated to split up the fraction as is, because the complicated part is in the denominator. And you can split up fractions more easily if you have a simple denominator and stuff in the numerator, because you can always write things with a common denominator. So that's kind of what we do here. Let's let u be equal to what that denominator is, x plus 5, and then du will actually equal dx. But we can solve for x also, right? If you subtract 5 from both sides, you get u minus 5 is the same thing as x. So we're going to be able to use that to replace the top, right? The top can be replaced by u minus 5, and the bottom can be replaced by just u. So now our integral becomes the integral of u minus 5, replacing the x on top, and u replacing the x on bottom, and then du and dx are the same, so you can replace dx by du. And now this can be computed using the common denominator trick. U over u is equal to 1 minus 5 over u du. And this is pretty easy to integrate. We just get u minus 5 times the natural log of the absolute value of u. Remember, the antiderivative of 1 over x is the natural log of the absolute value of x. And then we just want to switch back those u's to what they originally were, which is x plus 5 minus 5 natural log of absolute value of x plus 5 plus c. So that's finding the antiderivative using the u substitution method. Method 2, I would say, is using a bit more of sneaky algebra. So if you have the integral of x over x plus 5 dx, what we can do is we can actually add 5 and subtract 5 from the top, and that's really just the same thing as adding 0 in a clever way. So x plus 5 minus 5 over x plus 5 dx, and then we can split up the fraction now. So this is going to be the integral of x plus 5 over the denominator x plus 5 minus 5 over the denominator x plus 5 dx. And so then we're just integrating 1 minus 5 over x plus 5 dx, and this will have an antiderivative. Antiderivative of 1 is just x, and then we have 5 times the natural log of the absolute value of x plus 5 plus a constant. So notice the answers do not look completely identical, because in the method 1 example we have x plus 5 minus 5 natural log of x plus 5 plus constant, and down below we just have x. We don't have that x plus 5. Well, remember that c is an arbitrary constant, so c plus 5 would be arbitrary as well. So although the answers look different in terms of general antiderivatives, they're actually, in all matter of fact, the same. So let's go ahead and look at a couple more. Let's look at what will happen when we involve the definite integrals. We can actually do definite integrals as well. So really the only sneaky thing about definite integrals, definite integrals with u substitution. The only thing we have to do here is remember to change the limits as well. And if we do that, then we'll never have to switch back from u to x. We can just compute the value, because the answer to a definite integral is not a function or an expression. It's really just a number. So let's look at this example here. A couple examples, and what we want to do is we just want to evaluate. So let's say we do the integral from 0 to 1 of x squared times 1 plus 2x cubed raised to the 5th. I think we actually did this integral already, but now it's a definite integral, so the u substitution here is straightforward. U is equal to 1 plus 2x cubed. Du is equal to 6x squared. So dx. So du divided by 6x squared is equal to dx. So now we can replace the integral. But what we have to do is we have to replace the limits as well. So what's going to happen to the limits? Well, each of these numbers, 0 at the bottom of the integral and 1 at the top of the integral, are x values. So when x equals 0, you just plug it into u. U would equal 1 plus 2 times 0 cubed, which is just 1. And when x equals 1, u would equal 1 plus 2 times 1 cubed, which is 3. So we have our two new limits. So now our integral really looks like the integral from 1 to 3 of x squared times u to the 5th times du over 6x squared. So the x squareds cancel, so we get the 1/6 times this integral from 1 to 3 times u to the 5th du. So then we're going to get a u to the 6th, and then we have another 1/6 in front, so that's 1 over 36, and our integral is going from 1 to 3. So now we can evaluate that. So we have 1 over 36, and we have 3 to the 6th power minus 1 to the 6th power, and that comes out to 20.2 repeating. So that's exactly what that is. So it shouldn't be a squiggly equals. It's a regular equals. All right. So again, notice that we didn't have to substitute back from u to x because we changed our limit values from x values to u values, so we could plug them in directly once we found the antiderivative to figure out the value of the definite integral. Okay, let's try another one. Let's get some exponential functions involved. So we have the integral from 1 to 3 4x times e to the x squared minus 1 dx. So here we want to let u be the exponent, x squared minus 1, because when you take the derivative you'll get 2x. So du here is going to be 2x times dx, and then we can solve for dx by dividing by 2x. So du over 2x is the value of dx. And then again, we want to see what's going to happen to our limits. So when x is equal to 1, u will equal 1 squared minus 1, which equals 0. And when x is equal to 3, u will equal 3 squared minus 1, which is 8. So now we can change everything in our integral. So this will now be the integral from 0 to 8. We'll have our 4x, we'll have e to the u, and then we're multiplying by du over 2x. So 4x divided by 2x is just 2, so we've got the integral from 0 to 8 of 2 times e to the u du. And e to the u has a very easy antiderivative, it's just itself. So this becomes 2e to the u from 0 to 8. So this is going to be 2e to the 8th minus 2e to the 0. And this comes out, I'll round this one to 5,959.92. So that's rounded to 2 decimal places. Okay, so let's continue with 2 more of these. So let's say C, we have the integral from 0 to 1 of, let's say, 3t minus 1 to the 50th dt. So what do we have? Well, we want to let u be equal to 3t minus 1. So du will equal 3 times dt. So du over 3 is what replaces dt. Let's think about our limits. So when t equals 0, u will equal 3 times 0 minus 1, which is actually negative 1. And when t equals 1, u will equal 3 times 1 minus 1, which is 2. So our integral over here gets transformed. So it's now the integral going from negative 1 up to 2. and it's just going to be, so we have a 1/3, so it's u to the 50th times du over 3. So we just have a 1/3 in front, basically. So we have 1/3 the integral from -1 to 2 of u to the 50 du. So what we're going to do is we're just going to add 1 to that exponent, so it's going to be u to the 51st. And then in front, we're going to multiply by 1 over 51. So we get 1 over 3 times 51 is 153. And then we end up with u to the 51st from -1 to 2. So we get 1 over 153 times 2 to the 51 minus -1 to the 51. And then we can punch that into our calculator and we get some huge number. This comes out to something like 1.47 times 10 to the 13th. It's a gigantic number, so we'll just leave it in scientific notation. Okay, so let's go ahead and do one more. So let's call this part D. We're doing the integral from 0 to 2 of t squared times the square root of 8 minus t cubed times dt. So in this one we want to let u be what's underneath the radical. So we want to let u be 8 minus t cubed. And then du is going to be minus 3t squared times dt. So when we solve for dt, we get du over minus 3t squared, and that equals dt. We want to focus on our limits now. So what happens to our limits? So our limits, when t is equal to 0, I'll leave it for you to check that u becomes 8. And when t is equal to 2, we'll see that u actually becomes 0. So our integral up here is going to switch to the integral from 8 to 0 of t squared times the square root of u times du over minus 3t squared. So the t squareds cancel, and we get minus 1/3. That'll bring out front the integral from 8 to 0. And then remember, it's easier to integrate if we think of the square root of u as u to the 1/2. And then when we add 1 to the power, we're going to get u to the 3 over 2. And we're going to have to divide by 3/2, which is the same as multiplying by 2/3. So we get minus 2 over 9 u to the 3/2 from 0 to 8. And what do we get? We get minus 2/9, and we're going to get a 0. Oh, excuse me, we're going to get, oh, I flipped my limits. That's why something looked funny. It should be from 8 at the bottom to 0 at top. So when you plug in, you get 0, and then you're going to get minus 8 to the 3 over 2, and this will come out to 5.03 or thereabouts when you round off to 2 decimal places. Okay, let's go for one more example here, and then that will probably be it. And we'll maybe look back in another video at some sample homework problems. So if we look at part E here, let's look at the integral from 0 to 1 of x cubed over 3x to the 4th plus 1 dx. So then what's going on? U we want to let to be the bottom because the derivative of something raised to the 4th power will end up replacing something raised to the 3rd. So u is going to be 3x to the 4th plus 1. Du is going to be 12x cubed dx. So our du divided by 12x cubed will be the same thing as dx. Okay, we want to see what happens to our limits. So if we look at our limits, when x is equal to 0, u is going to become 1. and when x is equal to 1, u will become 3 plus 1, which is equal to 4. So now our integral, we can replace this. It'll go from 1 to 4. The x to the third on top we'll leave alone. The bottom of the fraction becomes u, and then dx is replaced by that du over 12x cubed. So our x cubes cancel. So I can bring the 1/12 in front, and I have the integral from 1 to 4 of 1 over u du. So as we know, that is going to be the natural log of the absolute value of u. So we get 1/12 times the natural log of the absolute value of u from 1 to 4. So we get 1/12 times the natural log of 4 minus the natural log of 1. And this comes out to about 0.1155. And that's it. So hopefully the process of using substitution is worthwhile. Sometimes it takes a little practice to understand if you're picking the right thing for you or not. But if you pick the wrong thing, essentially what's going to happen is you're not going to cancel out your original variables, your x variables. Once you solve for u and solve for dx and you replace those in the integrals, you should always end up with an integral that is only in terms of your substitution variable u, and that should be something that is transformed into a simple integral that you can compute. If it's a definite integral, you can switch the limits and then you can evaluate it down to where it's just a number. But anyway, that's it for this section. This is Dr. Lennon signing off.